Hello. Today we're going to look at nuclear physics, and in particular nuclear structure physics. We want to know what is going on inside the nucleus. In my video on the reasons for quantum mechanics, I showed that it had been demonstrated that an atom consisted of a central nucleus surrounded by orbiting electrons. The nucleus consisted of protons and neutrons. The number of protons in a given nucleus determines what the element will be. The lightest element is hydrogen, with 1 proton in its nucleus. The heaviest elements have about 100 protons in each nucleus, but at that stage the nucleus becomes unstable and begins to split into smaller elements. The problem is that apart from hydrogen, elements have more than 1 proton in each nucleus. Protons are positively charged, and we know from the Coulomb law that the protons will repel each other. That should mean that no nucleus other than hydrogen is stable. That clearly is not true. So what is holding the nucleus together? Perhaps it is gravity. The gravitational force might pull the 2 protons together and overcome the Coulomb force. But that is not the case. Doing the calculation shows that the attractive gravitational force between the 2 protons turns out to be orders of magnitude lower than the Coulomb force, and is effectively negligible. So what is holding the nucleus together? The answer is that there must be a force which we can call the nuclear force or the strong force, which is substantially greater than the Coulomb force. In fact, we can guess, since elements which have about 100 protons in their nucleus start to break up, that the nuclear force must be comparable to the Coulomb force, where you have 100 or so protons. The Coulomb force falls off as a function of r squared. This means that if you double the distance apart, the force falls off 4-fold. This is a force of repulsion. The nuclear force must be a force of attraction, but it clearly does not extend much beyond the range of the nucleus, so we can assume that the nuclear force will rapidly fall to 0 once we get beyond the radius of the nucleus. We can also assume that the nuclear force must itself become repulsive when the 2 protons are touching. Otherwise, the 2 protons would be forced to merge together. Finally, we know that the nuclear force must be significantly greater than the Coulomb force over the range of the nucleus. We can guess the shape of the nuclear force as something like this. But exactly what is the shape of the nuclear force, and what is causing it? These are the 2 key questions associated with nuclear structure physics. We can assume that there is some kind of interaction between the protons and the neutrons in the nucleus. There are 3 types of interaction: a proton-proton, a neutron-neutron, and a proton-neutron. Each must somehow exert a nuclear force on the other over a very short range. Calculating these forces for the impact of 1 proton or neutron in a nucleus on the many other protons and neutrons is very complicated. So in the early days, physicists resorted to modelling the nuclear force. These models were called phenomenological models. This is based on a macroscopic approach, which means we look at the whole nucleus as an entity, rather than the microscopic approach, where we try to calculate the interaction of each particle in the nucleus with every other particle. But before we look more closely at these models, we first need to establish how we are going to do any kind of experiment which will enable us to find out something about the nuclear force. We cannot look at the nucleus under a microscope because the size of the nucleus is far smaller than the wavelength of any visible light, and we would not be able to resolve that distance. The experimental method is known as scattering and involves taking some kind of particles, for example protons, accelerating them to very high speeds and smashing them into a target and looking to see how they scatter. There are various means of accelerating protons. A cyclotron works on the following principle. There is a circular chamber with 2 D-shaped electric plates. An alternating voltage is applied to the plates. There is a magnetic field above and below the plates. The protons, which are positively charged, will be attracted to the negatively charged plate and will accelerate towards it. But as the voltage changes, the protons will change direction. and because of the magnetic field, will end up moving in a circular orbit. The force on a charged particle moving in a magnetic field is given by F equals BQV, where B is the magnetic field, Q is the charge on the particle, and V is its velocity. Since this particle moves in a circle, that force must be providing the centripetal force. So BQV equals mv squared over r, where r is the radius of the orbit. We can rearrange this to give the velocity as bqr over m. The time for one orbit is the distance travelled divided by the speed. The distance for one cycle is 2 pi r. The speed is given by this formula, and so the time of the orbit is 2 pi r divided by bqr over m, which equals 2 pi m over bq. You will see that there is no radius term in this formula. As the proton accelerates, it gets faster, but as it gets faster, it moves into an orbit of larger radius, and so for any given voltage frequency, the time taken for a proton to go once round the orbit will be the same, irrespective of its speed, because its additional speed will be compensated for by its larger radius. Eventually, the proton will be moving at very high speeds and with very high energy, and can be released from the chamber at high energy and high speed down a tunnel where it can smash into a target. There is a limit to the amount of energy which can be given to a proton in a cyclotron. The maths will not work if the proton starts to assume relativistic speeds, that is, if it gets close to the speed of light. For practical purposes, the maximum energy available to a proton in a cyclotron is 20 MeV. An alternative means of accelerating particles is a linear accelerator. In this case, we simply have a very long tube with electrodes placed along the tube. Every other electrode has the same charge. The other electrodes have an opposite charge. An alternating voltage is applied. The electrodes change polarity, so the proton is progressively accelerated towards the next electrode, which has become negatively charged. The particle's speed increases each time it passes an electrode. Finally, the Large Hadron Collider in Geneva is a 27-kilometre ring buried underground. Magnetic fields are used to cause the protons to circle around this tube at very high speeds, extremely close to the speed of light. The protons are sent in both directions around the tube and then can be brought together so that they are smashed into one another at extremely high energies. It is estimated that those energies are comparable to the energy that was around well within the first millisecond after the Big Bang. What happens when particles such as protons smash into their targets? The energy of the proton is sufficient to overcome the Coulomb repulsion and get it very close to the nucleus in the target. It will therefore experience both the Coulomb force of repulsion and also the nuclear force of attraction. The incoming particle, if it gets anywhere near a nucleus, will in some way be deflected. Of course, since the target, which is a very thin piece of an element, is made up of atoms, and since the nucleus is only 1/10,000th the size of the atom, most particles will travel straight through the atom without getting anywhere near the nucleus. But it is the ones that get close to the nucleus that are of interest to us, and they will scatter over a whole range of angles. By measuring the number of particles scattered according to the angle of scattering, we can start to build models that will explain how that scattering could have come about.